Okay, welcome back, everybody. Just a quick announcement. As you probably noticed, I'm not complete with grading the exam. I have all of those, everything else cut up this weekend, so bear with me. Any questions? Any questions, comments, concerns? We are on chapter 10, folks, and you know we're getting close. You know, pretty. I think this is the 9th week, so we're about halfway done. And anyway, if you need assistance, again, email me. Again, we have tutoring. Dr. Dana and Dr. Kim are running sessions to help you with the questions and so forth. So take advantage of them. Okay, take advantage of these resources for you. All right, well, let me go back. We ended up in chapter 10. Now here again, we're talking about chemical reactions. And of these chemical reactions, there's only 6 types of a couple that I've already introduced you to. Well, it might be too bright there. Any better. Okay, so I'll work in the dark here for a bit. And so let's go over them. Now, what I've done here is I'm showing the 6 types of chemical reactions in general terms, okay? In general terms, to kind of give you a perspective of what to look for when you look at a reaction and to see what is happening. Now, you can see here we have 2 reactants. We got A and B. 99% of the time, those 2 reactants are, elements, okay, of some sort. What they're going to do is they're going to combine together and to create a compound. Remember, the definition of a compound is 2 elements, 2 or more different elements coming together. Okay. All right. There's a little bit better. And so here you have 2 elements coming together to form a compound. That's an example of a combination reaction. Okay. Second example is basically the opposite of a combination reaction. Whereas combination reaction, 2 elements come together to form a compound. Here, we start with a compound, and it's shown here ABC. It could be 2 or more, okay, but different elements. Something happens to them, we do something, and we actually break them down back to the elements. A classic example for the combination reaction would be, for example, hydrogen gas and the presence of oxygen to generate something that we all need, H2O, water. But in the same token, I can take water and I can hit it with some energy, specifically run a current through it, and I break it down back to the elements, in this case, hydrogen and gas. And that's why it's so crucial that we find water out there in space, because we can break it down to create oxygen that we need to breathe and hydrogen that we can use as fuel. Okay. Combustion reaction. Now, notice here, let me clear. Notice that we have a compound of some sort, which is made up of nothing but carbon and hydrogen. Okay. We call these hydrocarbons. Gasoline is a good example. Any fuel, any hydrocarbon, any gasoline is a good example, and that is made up of nothing but carbon and hydrogen, hence the term hydrocarbons. Now we're going to deal for Chem 130 with the combustion of simply hydrocarbons. That's it. Okay. Now, one of the key components or reactants for any combustion, as you well know, is you need oxygen. Without oxygen, that hydrocarbon will not burn. You will not get your engine to work if you don't have no oxygen. Okay. Now, with respect to Chem 130 again, for Chem 130, the only two products you will get from a combustion reaction will be carbon dioxide and water. True, you burn fuel on an engine, and one of the gases that you generate, which is a poisonous gas, is carbon monoxide. But that's because our engines are not very efficient with respect to combustion of our hydrocarbons. And therefore, there's a lot of variety of different types of compounds that are generated when we combust hydrocarbons. But for us, remember, carbon dioxide and water are the only two products we obtain. Now, with respect to balancing, we're going to talk about this. When we balance this type of reaction, we have a very specific steps to do where we can balance a combustion reaction. The decomposition and the composition, let me restate that, the combination reaction and the decomposition reactions, those probably the majority of the time is a trial and error of that, adding the numbers here and then going back to reactants or products and playing with the numbers to get it to balance, okay? With combustion reactions, we have a more systematic approach with respect to balancing it. Now, normally the combination reactions and the decomposition reactions that we work with are not very complicated. So a trial and error is a very straightforward way to balance those type of reactions. All right, next reaction is an acid-base reaction. And we've talked about this already with the acid-base chapter. And here we have a general acid denoted by H first and followed with whatever A may be, like nitric acid, hydrochloric acid. And then we have an ionic compound that has a polyatomic ion, which is the hydroxide, okay? Now remember the reaction of an acid-base reaction, AKA neutralization reaction. We have a proton plus an hydroxide reacts to give you water. You have neutralized both the acid part and the hydroxide part to produce neutral or pH 7 water, neutral water, okay? And so always remember this, acid-base reaction, always produce water, okay? And then the other product is simply the corresponding salt, depending on what the metal is. So M represents the metal that combines now with the anion. So the cation of the base combines with the anion of the acid to form some salt. And salt, again, is not just always sodium chloride. Salt in chemistry is an ionic compound, a metal-non-metal combination, okay? Now, to balance these reactions, when we balance these follow the proton and the hydroxide. Balance those guys first, and everything else will fall in place. So you balance the hydroxides and the proton and the water, and then the salts themselves will come in and just balance themselves. Okay. All right. We have what's called a single replacement reaction. Now, what happens here, you take a metal of some sort, it is the element, the metal, and then you take let me regroup here for a second. You take a second metal that happens to be in ionic form. You can see this is ionic compound here. A represents the second metal, M represents the first metal. Now, depending on the reactivity of these two metals, you may or may not get a reaction. In essence, what happens is the metal, which has a zero oxidation state, is releasing some electrons, losing electrons like metals do, but the A in this case picks them up to form A in the form of an element, okay? And then the M replaces the A in the ionic compound. So you get a new ionic compound, which is MX. A classic example here would be plating. I'm sure you all heard of plating, chrome plating. You got some bump, something that you're gonna want shiny, copper plating, or gold plating. And generally you have a process where you're taking that metal that you want to plate onto some surface that's in ionic form and then convert it into elemental form on some surface, okay? Now, to identify this reaction, to be able to determine whether a reaction proceeds or not, we're going to have a systematic approach again, in which we're going to ask some questions on these two metals to determine whether a process, that process, the way it's written, will work. And we utilize the periodic table. On the right side, there is what we call a activity series, okay? Not necessary to memorize it because you have it there, activity series. And in essence, what the activity series is telling you is straightforward. It's saying that if we look at lithium, for example, lithium is more reactive than potassium, which is more reactive than barium, which is more reactive than strontium, so on and so on down the road. The least reactive metal is the very last one, which is gold. We know that gold is also known as a noble metal because, like noble gases, they're not very reactive. And gold can sit under the ground for thousands of years and come out as shiny as it was when it was placed under the soil. Okay, not that it doesn't react, but it just takes very vigorous processes to get gold to react. And so this is our reference guide. Now, note that the first set, 1, 2, 3, 4, 5, and 6, all the way up to sodium, from lithium to sodium, they are underscored and they're in bold. Those guys are extremely reactive. They simply just fall into water, for example, and boom, you get a reaction. Sodium metal, if that touches water, you get a very aggressive reaction. You generate a lot of heat and a lot of hydrogen gas, which then can explode because of the hydrogen gas in the heat. The other metals that are not in bold are not as reactive, okay? And require just a little bit of acid, for example, to get magnesium and aluminum to react. Now, the reference point you see here in parentheses is hydrogen gas. That's how this is a relative scale, okay? It's relative to hydrogen gas. And H can be in the form of, the elemental form of hydrogen, as you know, is H2, but it can also be in the form of the proton or possibly water. Now that's important because we're going to ask one of the questions, and the questions we're going to ask is the most reactive metal / hydrogen, is it in ionic form? And if the answer is no, reaction proceeds. And the ionic form of hydrogen will either be in the form of H+ or in the form of water. Okay, obviously H2 is the elemental form. So we're going to do some examples of using the activity series to help us to predict a particular reaction that is presented to determine whether that reaction will work. And then, of course, we balance them. And in this case, normally it's a trial and error, very simple reactions, not too complicated, like the combination and decomposition reaction. And finally, this is an example of the one we did in the previous slide where we have looked like a very complicated reaction, and it is. However, let's simplify it, okay? What we have here are obviously ionic compounds. They're both a combination of metal and a non-metal, so they're ionic compounds. Furthermore, the reactants are, both of them are based on the solubility rules, soluble in water. Okay, so both M1, which is bonded to some anion X, and M2, which is bonded to some metal Y. Now, that subscript 2, no, it's not saying 2 M's. No, the subscript here is just saying it is different from the first metal, okay? Just different. So, and if I were to put it up in the superscript, it probably you might think it's this charge, but it's not. So maybe best rearrange that and give it a different letter, like the letter M, N. All right, so subscript here does not represent the number of metals that you have. They're both of them are aqueous, they're both soluble based on the solubility rules. You put them in solution. Normally, you got two test tubes, 2 beakers of clear solutions. You mix them together. If it's a positive reaction, you get what is a precipitate. You get a solid. And the products here, whether a reaction proceeds, are dependent on the solubility rules. Okay. Now, for example, if M1Y, notice that M1 used to be partnered with X. Now they just exchanged partners, made a new compound. If M1Y is insoluble, based on the solubility rules, then we get a reaction, okay? If M2X is also insoluble, obviously we got a reaction. If any of these 2 products are insoluble, we got a reaction. If both of the new products are soluble, okay, no reaction. If both of the products are soluble. Now, we don't care about the solubility of the reactants, we care about the solubility of the products, okay? Now, to balance these, like we did in that example of that slide, we follow the polyatomic ions. You follow those polyatomic ions, most of them will have you follow the anion, and you'll see that they will balance out by themselves, okay? We'll do some more examples of these. All right, so in a nutshell, you can see that this is a table representing general compounds reacting to form a product. Okay, we're not talking about specific examples. Okay, well, let's take a hold of a combination reaction. For example, we did notice the combination reaction. We have two elements reacting to form a compound. And don't we have that here? We got phosphorus in the presence of oxygen, which are 2 elements. They combine to form P2O4, okay? And so we need to balance it. And there's multiple ways of balancing it here, but as a general guideline to help you out, when you have an element that's not diatomic and it's sitting there all by itself, leave it alone, save it for last, and work on the other. And so here we got 2 oxygens on the left side, 4 on the right side. We simply put a 2 there, and that takes care of the oxygens. We can see that we got 2 phosphorus, so we simply put a 2 in front of phosphorus, and we are balanced. Okay. Make a note, the relationship between the phosphorus and the oxygen is a 1-to-1. That coefficient in there is a 2-to-2 ratio, which is the same thing as a 1-to-1. Okay. And the ratio between the phosphorus and the product, diphosphorus tetroxide, is a 2-to-1. Between oxygen and the product also is a 2-to-1. So these are the ratios that you just be aware of them and be familiar with them, because we're going to use that relationship in the subsequent following chapters. So there's an example of a combination reaction, 2 elements coming together to form a compound. Okay. Now, decomposition reaction. If you go back to the table with the general reactions, you'll see you start off with a compound, you do something with it, and you generate the 2 elements. And so here, We have iron 3 oxide. Okay. And that is AKA rust, FYI. That is decomposed back to the iron element and back to oxygen. Okay. All right. So we got to balance it. And, you know, we have, okay, here we go again. We have an element all by itself, a monatomic element. We have, you know, so we leave that alone for last. Look at the other reactant, oxygen diatomic. Let's balance those. So we got 2 here and we got 3 here. All right, we look for a common number. So if I put a 2 in front of iron 3 oxide and a 3 in front of oxygen, guess what? I balance my oxygens. They're happy. But then my iron gets kicked up to 4. Okay, so no problem. I put a 4 in there in front of iron and it's balanced. Note the ratios. It's a 2 to 4 between the iron 3 oxide and iron. Okay. It's a 2 to 3 ratio between the iron 3 oxide and the oxygen. And between the iron and the oxygen, there is a 4 to 3 ratio. Okay, you may need to know that information. Okay, there we go. And don't forget the physical states are given to you. Okay, now we have combustion reaction. And recall from the general table, when we deal with combustion reaction, we're dealing simply only with hydrocarbons. Note the formula there. You got 3 carbons and 8 hydrogens. FYI, if you're gonna do some cooking this weekend on the grill, that's what you're gonna be burning. Propane. That is the general formula for propane. Structurally, I'm just going to give you this just for information purposes. It is 3 carbons that are bonded to each other, and then the hydrogens are all distributed around. Okay, so that's propane. If you have a lighter, flick your Bic, just add another carbon there. And you have butane. Okay, and just again also replace, just add some hydrogens because we're dealing with hydrocarbons. So you got, you know, butane, propane. Now you know what you're burning, and obviously the fuel that you burn are very large. You know, octane. Can you imagine? Oct is 8. Ane indicates a hydrocarbon. Okay. So we have propane here. So the things, the wording may be, okay, the combustion of this hydrocarbon, you know, write the balanced chemical equation for the combustion of C3H8. Okay, no problem. It's a combustion reaction. We're going to note that. That tells me that somewhere I'm going to use O2 because I need to burn something, right? That also tells me that the products, remember, the products are always going to be CO2 plus H2O. That's it. Okay. I'm given the hydrocarbon. It is C3H8. It's going to react with oxygen. It's a combustion reaction. All right. Hit it with a spark. All right. Down here's the space fill model of propane. And like I stated, combustion reaction, only products I get, carbon dioxide plus water. Okay. Now, normally, when you're doing a combustion reaction, everything here is a gas. Okay. Even vapor, water vapor. That water that's being formed in here, you know, it's pretty hot. And so it's no longer liquid. It's going to be in the gas phase. So everything is a gas. All right. That's the reaction, the combustion reaction of the C3H8. hydrocarbon. Now we got to balance. Step number one, balance the carbons first. Carbons get balanced first, okay? Normally it's in the reactant side. We can see we got 3 carbons there, okay? So we go to carbon dioxide. That's where the carbons have been now changed to. We simply put a 3 in front of carbon dioxide. Number 2, balance the hydrogens next. Okay, so you can see in reactant side, we got 8 hydrogens. So we need to balance these 8 hydrogens. The hydrogens are in the form of water now as products. So I can simply put a 4 in front of H2O, and that gives me 8 hydrogens. So my hydrogens are balanced. My carbons are balanced, okay? So, and I got 3 carbons over here. And so they're happy now. Carbons, hydrogens are okay. And then number 3, finally balance the oxygen. So we go to the product side and we tally them up, because most of the time, you know, you got carbon dioxide all the time, I should say, carbon dioxide and water. So that oxygen is distributed between 2 compounds. So here we got 3 carbon dioxides. That means we got 6 oxygens in the form of carbon dioxide. And water, we got 4 molecules of water. So we have 4 oxygens in the form of water. So total, we have 10 oxygens on the product side. Okay. So we go over to the reactant side, and we simply just take that 10 divided by 2, excuse me, to give you 5. Because the oxygen is diatomic. And this is where it's important to remember that oxygen is diatomic, because if you wrote it like this in the reaction, you're incorrect already, which also tells you that you need 10 O's, which is incorrect, okay? So that's where the states of the reactants and products are important to know, especially the diatomic ones. And so now we got 10 oxygens on reactant side and 10 on the product side, and good old-fashioned Mother Nature is happy. So overall, it takes 1 molecule of propane, C3H8, 5 molecules of oxygen, okay? And what that does, it creates 3 molecules of water and 3 molecules of carbon dioxide and 4 molecules of water. And all that goes into the atmosphere. And yeah, quite a bit of oxygen is used up for that 1 molecule. Let me clear my drawings and we'll give you the balance term equation a little bit neater here, all printed out. All right, so yeah, notice that it takes 5 molecules of water to burn 1 molecule of, in this case, propane. And that creates 3 molecules of carbon dioxide and 4 molecules of water vapor. All right, that is a combustion reaction. Okay, so, and what this does here is go over what I just said about balancing it. Balance the carbons first, okay, followed by balancing the hydrogens, and then finally at the end, balance the oxygens. Remember that you're going to be combusting simply a hydrocarbon with oxygen, and you're always going to get carbon dioxide and water. All right. Acid-base reactions, we had talked about this when we did talk about acid-base reactions. And this formula, general formula here should look familiar. We have HA, which is general acid. MOH, which is a general base. We know it's a base because it will produce hydroxide in solution. Okay, so we have the proton source here, a hydroxide source here, reacts to give us water. Okay. So let's complete the reaction. HCl, we got a hydrogen written first. Again, that helps you with it to indicate that you have an acid. The only exception to that is H2O. Notice hydrogen is written first. And I stated that earlier, that it is just by convention. It doesn't mean it is an acid. But I would say 99% of the time when you see hydrogen written first, you're working with an acid, okay? Eventually you start picking up on who are the acids and who are the bases and so forth. So we got hydrochloric acid, same acid that's in your stomach. Then you react it with barium hydroxide. Barium hydroxide is a base because you have hydroxide is being created, okay? Now, two things to remember. For every one proton that you generate, you're going to need one hydroxide to give you one water, okay? Notice that hydroxide here has two hydroxides. That tells you that I need two protons. You neutralize the two hydroxides that are going to come from the barium hydroxide that goes in solution, okay? And if I have two protons and two hydroxides, guess what? How many waters I'm going to make? How many waters am I going to make in this first example? Anybody know? Anybody want to tell me how many waters? I'm going to get waters. There's no question about it. Question is how many? Given this information up here. Anybody have any idea? If I have two protons and two hydroxides, how many waters am I going to make?
2.
You got it. Okay. 2 waters. Plain and simple. Remember, for acid-base reactions, when we got to balance them, follow the proton and the hydroxide. All right. Now, as we see from the general reaction, we got the salts that are being created. And so that, let me change the color here so make it a little more visible. We got the cation of the base and the anion of the acid. So put them together first with respect to their charge. We know that barium has a +2, right? If you don't know, look at the hydroxides. The hydroxides each have a -1, and there's 2 of them. That must mean that barium must be a +2, okay? Additionally, barium is a group 2 element, therefore has 2 valence electrons, and then as it loses those 2 electrons in ionic form, it would be a +2 charge, okay? Now, the anion from the acid, we know it is chlorine, is in group 7. When it becomes chloride, it gains 1 electron. Trying to maintain that magical 8 number. And so we have 1 chloride. So now I'm going to put barium and the chloride together, and I need 2 chlorides to counter the +2 of the barium. So write the salts first in ionic form to make sure, just like we did before, writing the formulas, to make sure you put them together correctly with respect to their charges. So the formula is BaCl2. And check this out. If we look at the barium now, barium, we got 1 barium over here, 1 barium over here. We got 2 chlorides in the form of barium chloride, and guess what? We have 2 chlorides in the form of hydrochloric acid, okay? So the proton and the hydrogens, you're not sure about the hydrogens, even though we follow water, we got 2 H's coming from hydroxide, and 2 H's coming from hydrochloric acid. We got a total of 4 hydrogens. What do we got here? We got a total of 4 hydrogens in the form of water, okay? So by following the acid and the base, we balance the oxygens and the hydrogens. And then the salts just come into play, just fall in place. Let me clear this up a little bit. That shows we got, oh, and of course I forgot to put in the Physical states. Remember, when you generate water, these acids and base reactions are occurring at ambient temperature. Okay, and so forth. Therefore, you are making water, which is in liquid, right? So its physical state is water, is liquid L. The barium chloride, its physical state based on the solubility rules is soluble, and therefore we put AQ. Okay. All right, now we got a different one here. A little more challenging, but let's break it down. I think we can figure it out. All right, we have H3PO4. If you recall, that was phosphoric acid. Okay. Now, how many protons will phosphoric acid generate when it goes into solution? What do you think? This guy right here. When H3PO4, which is an acid, goes into solution, how many protons does it have? Does it generate, will make? What's that subscript tell you? Yeah. Anybody want to take a wild guess how many protons phosphoric acid creates? You don't have to guess, it's right there. 3. Okay. HCl, when it went in solution, only generates 1 proton. H3PO4, an acid, will generate 3 protons. How many protons will sulfuric acid generate? H2SO4. How many protons? Anybody want to answer this one? How many protons will sulfuric acid generate when sulfuric acid goes in solution? Or every reaction with the base? How many protons will it have to react with? 2. Okay, you have to recognize those because that's the only way you're going to be able to balance these reactions. Let me clear up the mess a little bit. And so phosphoric acid has 3 protons, so it's going to make 3 protons when it reacts. Now, how many hydroxides does calcium have? Calcium hydroxide. How many hydroxides will calcium hydroxides have when it goes in solution? What's that number right there? Okay, it's going to generate 2 hydroxides. Okay, well, let me ask you this. I need to neutralize all the protons and all the hydroxides, but I got a problem here. I got 3 protons and 2 hydroxides. What can I do? So I get enough protons and enough hydroxides to neutralize each other. Because if I just leave them like that, 3 protons and 2 hydroxides, well, 2 of them are going to react. I got a proton left over, has not been neutralized. So how many phosphoric acids do I need so I can neutralize an X amount of calcium hydroxide? Remember when we were putting formulas together? Okay. And I said, okay, I want to add these 2 fractions. How do I do that? What was I looking for? When I add 1/3 plus 1/2, what do I look for?
The common denominator.
Exactly. So in that 1/3 plus 1/2, my common denominator is 6, right? Everybody agree on that? Right? So I need to convert the 1/3 to 6 and the 1/2 to 6. Now, do I have a similar situation here where I got 3 protons and 2 hydroxides? Yeah. So I got to find a common factor here. So what if I put a 3 in front of barium hydroxide? Oh, excuse me. Sorry. A 3 in front of calcium hydroxide, because wouldn't that give me 6 hydroxides now? Yeah. And what if I put a 2 in front of the phosphoric acid? Wouldn't that give me 6 protons now? Yes, it will. Just like we did over here, just like we did when we were trying to put together the formula here. We looked for a common number here. It happened to be 6. So we needed 2 iron, 3 threes, and we needed 3 oxides to get that formula coming together. We're doing the same thing here. So meaning that I got 6 protons now and 3 hydroxides. Anybody want to take a guess of how many waters I'm going to make now? If I have 6 protons and 6 hydroxides, how many waters am I going to make? Remember the ratio? 1 proton plus 1 hydroxide gives me 1 water. And so if I have a billion protons, how many hydroxides do I need? I need a billion hydroxides to neutralize the billion protons. How many molecules of water am I going to make if I have a billion protons and a billion hydroxides? Do I not, am I not going to make a billion? Yes. All right. And so if I got 6 protons, 6 hydroxides, how much water am I going to make? How many molecules of water am I going to make? Anybody want to take a shot at that? How about 10? Would I make 10? How about 20? Oh, somebody got it. Let me see. 6. Okay, Jaylene, thank you. You're correct. You do make 6. Okay. And the point I was trying to get when I said a billion was this. It's a 1-to-1 ratio. These ratios are, you got to grasp that concept. When these ratios, we start working calculations, they're going to be very important. And so if I have 1 proton and 1 hydroxide reacting, I get 1 water. That means I can take that 1 and just multiply by a quadrillion. So if I got 1 quadrillion protons, I need 1 quadrillion hydroxides, which will make me 1 quadrillion water molecules. So here, we will create 6 molecules of water. Okay. And guess what? We have the protons and at least some of the oxygens balanced. Okay. And I say some because the phosphates come into play. All right. Now we have to put, remember, we got to take the cation and the anion and put them together. Okay. So this is where we write the ions. So PO4 is a -3. That's the phosphate ion. And calcium, we know it is in group 2. So it has a +2 charge. And lo and behold, we got a dissimilar number again. We got a -3 and a +2. So no big deal. That means we need our common number is 6. So we're going to need 3 phosphates for a total of -6, and we're going to need, 2, and 3 calcium ions for a total of +6. And so our formula now becomes Ca3PO4 -2. Okay. Just like we've been doing before. Nothing new here. Notice how everything's tied in together. Remember, we were writing formulas and we had dissimilar charges. We look for a common number and then we put them together. Okay. So now let's check to make sure that we are balanced. And so we have 2 phosphates coming from phosphoric acid. Guess what? We got 2 phosphates right here. We got 3 calciums in the form of calcium phosphate, and we have 3 calciums in the form of calcium hydroxide. Let me clear it up a little bit and look at the numbers through there. And this is going through, follow the protons first. So you end up making 6 molecules of water. Okay. And if you check that, everybody is balanced. Okay. We have 6 hydrogens here. And then here we have 6 hydrogens in the form of calcium hydroxide. There's 3 molecules of calcium hydroxide. Every one contains 2 hydrogens. So we have 6 hydrogens. So we have a total of 12. Okay. So look at this. 12 hydrogens over here. Oxygens, I got 8 oxygens coming from phosphoric acid and 6, excuse me. We got 6 oxygens coming from calcium hydroxide. So it's a total of 14 oxygens, right? And so if we look at here, we got 8 from the phosphate and 6 in the form of water. So that's a total of 14 oxygens. So oxygens are balanced, hydrogens balanced, phosphorus is balanced. We're good to go. And we did that by following the proton and the hydroxide as far as balancing acid-base reactions. All right, this brings us to the single replacement reaction. And in that example, in that general example, we have a metal M reacting with an ionic compound with another metal designated here as A. It's an ionic, AX, X could be anything. And then if this reaction proceeds as written, they'll be exchanging the metal. So the metal, which was an element, now becomes ionic. Okay, it starts off as an element and then becomes ionic. A is ionic to begin with, because this is a ionic compound, but then becomes an element after the reaction is done. Okay, so we've exchanged the metals. So M and A represent metals. Okay, let's. Oh, somebody had a question. I heard something. Okay, so in this case, we use the activity series as I mentioned. And here's the activity series again. The ones in bold white represent those metals that are extremely reactive. They react with water spontaneously. And starting from magnesium to lead, up to hydrogen, those will react if you add a little hydrochloric acid to them, make it a little bit stronger. But copper, once you pass the hydrogen, which is in parentheses there, but once you get up to here, copper, silver, and gold are pretty much unreacted. They require some vigorous conditions to get them to react, okay? And again, thing to remember, this is a relative scale, and it's relative to hydrogen gas, which is the elemental form, and then the other ionic form of hydrogen is either the proton or it could be in the form of water. Okay, thing to remember. So this is the ionic form on the right, the elemental form on the left. And the reason I say that, because you're going to ask the question, which metal is the most reactive metal in ionic form? Okay, let me clear this up. Let's go back to this reaction. If, for example, we were looking at this reaction, what we do is, number one, we ask the question, most reactive metal. We go to the activity series and we find that M is more reactive than A, okay? That's from the activity series. And we compare the metals regardless if they're ionic form or not, just the metal. So the metal M, metal A, find its position on the series. Then determine which one's more reactive. So then you ask the question, is the most reactive metal in ionic form? Okay, so the question is the most reactive metal already a compound, specifically an ionic compound? And that's the question you ask between M and A. If M is most reactive, here, the way it's written, the answer would be no, because M is in the elemental form if M was more reactive than A. So then that means yes, reaction occurs. Yes on the reaction. And that reaction as written proceeds. If it's the other way around, and we say that A is more reactive than M, well, what happens then is 4 becomes no reaction, because the most reactive metal is already in the most stable state for it, and it's in ionic form. You see how that goes? So we find the most reactive metal, determine if the most reactive metal is in ionic form, is it a compound? If the answer is yes, then we don't go anymore. It's done. It won't react. If the answer is no, reaction proceeds. Okay, so let's do some examples. Okay. And this is, in essence, what I just explained. Check the activity series, which is more reactive. And sometimes it could be hydrogen gas. You could be comparing a metal in the reaction of either hydrogen gas or a proton, okay? Write the states, not to forget the states, exactly. And then balance, of course, we're going to balance the reaction. So let's take a look at this reaction. We have zinc nitrate plus sodium. And the question is, it's asking you to determine whether this reaction will proceed. So step number 1, we identify zinc on the activity series, and there's zinc, and there is sodium, okay? And so we determine the most reactive metal here is sodium. Sodium is more reactive than zinc, okay? So second question, is the most reactive metal in ionic form? Here in this example, the answer is no, okay? No on sodium, because sodium is an elemental form. What that means is the reaction will proceed. So sodium will replace zinc, and zinc will become elemental, okay? So I'm gonna write we will get zinc solid. And the sodium now becomes elemental. So first, like we've been doing, write sodium in elemental form. We know sodium will have a +1. The nitrates will have a -1 right here. Nitrates, you go to again, periodic table. If you forget, look up the nitrates and the polyatomic ions. All right, so that means that we can put the sodium and the nitrates together as a 1-to-1 because they balance each other's charge. Correct, as a 1-to-1. Okay, and so now we have zinc nitrate, okay, plus sodium, rewriting the equation. We wrote that yes, a reaction will proceed because the most reactive metal is not in ionic form. Therefore, reaction proceeds. And we generate zinc, elemental zinc, and then we replace the zinc with sodium. Now it becomes sodium nitrate. Now we're going to balance it. So notice we got 2 nitrates to begin with. So if I put a 2 in front of sodium nitrate, that balances the nitrates, which kicks up my sodium, and no problem. I go back to the element and put a 2 there. And now I am balanced. I got 1 zinc, 2 nitrates on the right, 2 sodiums on the right. So we have a balanced chemical equation. And let me get the clear one here. Now, with respect to the states, that's where the solubility rules come into play. We know that the top 4, remember, lithium, sodium, potassium, and ammonium, anything bonded to those 4 are soluble. So the sodium nitrate is soluble. Zinc is a metal, okay? And we know that of all the metals, there's only one metal that's a liquid, and zinc is not one of them, so it's a solid. All right. So we have a balanced chemical reaction here. Note the ratios, 2-to-1 for zinc nitrate, 2 sodium metal. Of course, it would not be sodium nitrate subscript 2 because sodium ion is a +1, not a +2. All right, let's take this one. Okay, who can tell me which metal is more reactive, strontium or aluminum? Which one is more reactive? That's the first thing you got to do. You got to determine which metal is more reactive. And we're comparing SR versus aluminum. We don't really care if they're ionic form. We're just comparing metal to metal, regardless of it being whatever form. So what do you got? Yes, it is. You are correct. So what we know is this: strontium is more reactive than aluminum. Pure strontium, in fact, it's one of those metals that you just put in water and they will erupt. There's strontium and there's aluminum, okay, using the activity series. You don't have to memorize this series. It's right there in the table for you to use, okay? You will with time. If you do quite a number of these, you eventually know which one is more reactive. And so strontium is more reactive than aluminum. Now, second question, is the most reactive metal in ionic form? It's either yes or no. Is strontium, this is the most reactive metal in ionic form? Is strontium a compound? The way it's written in the equation. Here. Is strontium a compound here or an element? It's, I think I heard somebody say, yes, it's ionic. It is an ionic form. So the answer is yes. Okay. If the answer is yes, that means that it is in the most stable state. The most, what it's doing, let me put it to you this way. The most reactive metal, when you're comparing two metals with each other, wants to be in a more stable state. And for that to happen, it wants to go into ionic form, okay? And so in this case, the most reactive metal is already in the most stable form, which is ionic form. And so what happens is no reaction, okay? No reaction here, nothing will happen because strontium bromide is already as an ionic form. It's stable, it's happy. It's got the octet fulfilled there, okay? So what does that mean? Here's a little something for you. If the way it's written says no, guess what? The opposite process will react. So instead of strontium bromide, what if we had aluminum bromide plus strontium element? Okay, which is the opposite of what we're given. In this case, yes, we would get a reaction to give us strontium bromide plus aluminum. I will balance it here. Okay, you guys can. Okay, see how that works. So if one direction the reaction says no, it's not going to happen. Keep in mind, then the opposite will work. In other words, the aluminum in the form of aluminum bromide and the strontium bromide in the form of strontium, the element, means yes for the reaction. With the same questions, with the same questions being asked. All right. So strontium is more reactive, and you know it's already. We have this reaction. We got aluminum and H hydrochloric acid. We gotta think about this, right? Well, not really. Think about it. Let's go back to the activity series here. Here's aluminum, and here's hydrogen. So aluminum is more reactive than hydrogen. Okay. So and then the second question here, aluminum, in this case, aluminum is more reactive than hydrogen. And in this case, it could be hydrogen or H plus, hydrogen gas. And then aluminum is not in the most stable state. Aluminum is an elemental form. The most reactive metal is an elemental form. So the answer is yes for a reaction. Okay. And so H plus, that is the ionic form of hydrogen, will generate H2. Okay, we're exchanging partners here. No different, just because we got hydrogen. Normally we've been doing two metals and two metals, but here we got hydrogen because that's our reference point on that series. And so we have aluminum is going to become ionic, so that's Al plus 3, and we still got the chlorides. Okay, so we're going to need 3 chlorides for every aluminum ion. So we got AlCl3. Okay. And now we have to balance it. Clear that out. So here's the the reaction, a hydrogen gas is being generated. Okay. And then we balance it out. We got the following. Oh, you got the physical states. In fact, if we look at the activity series, here's hydrogen. Right here. So obviously for the metals from magnesium to lead, and if I treat that, I just call it M, reacting with, we're going to call that HX, which is an acid. We're going to end up with hydrogen gas plus MX, whatever that metal is, okay? Now, these that are in white are very reactive, and like I stated, they react with water first before they react with hydrogen. So what happens there, I'm going to call those, again, M plus H2O will react, and what happens, you get M hydroxide plus H2 gas, okay? With the ones that are in both, very reactive, and a lot of heat. Let's separate. This would be M prime. Okay, so those very reactive metals will react with water to form the hydroxide, the M hydroxide, M prime hydroxide. It could be lithium hydroxide, potassium hydroxide, strontium, barium, calcium, or sodium hydroxide, plus hydrogen gas, okay? Remember I said the hydrogen, the elemental form, as you know, is H2, and the ionic form of hydrogen is either in the form of proton or H2O. And so for this reaction, the hydrogen, the metal is a lot more active than hydrogen, and the metal is going to go into ionic form. And the water now goes into its more stable form, which is the element gas, okay? Here is mud, huh? All right, so we got that. Now there are, of course, there's are the YouTube videos that we have concerning the activity series and how to work through these reaction compounds. So yeah, watch them. A lot of good information on there from Dr. Kim. Okay. Now, with respect to the activity series reactions, the single replacement reactions, there's a flow chart. You figure out which is more reactive. I should add metal, the most reactive metal / hydrogen. Okay. Is it in salt form? If the answer is yes, then you get no reaction. If the answer is no, then the reaction proceeds. You exchange the position of the metals. Which brings us to the last reaction, which is double displacement reactions. We went through this example earlier, okay? And in both cases, we got AX, BY. We have aqueous solutions. There are soluble solutions, different metals, okay, and anions, so different compounds. Now they will react. They essentially just exchange partners. So where you had AX before, notice you have AX, and now you have AY, okay? And where you had BY before initially, now you have BX. And what drives this reaction is that one of these will have to be insoluble based on the solubility rules. If both of them are soluble, the products, no reaction, okay? Gotta have at least one of the products insoluble. Okay. We call this a precipitation reaction, double replacement, because you actually see a solid. In fact, we do a lot of this when we're looking for particular chlorides, for example, in your water sample or some other things in your water. A precipitate is a positive for whatever element you're looking for or ion you're looking for. Okay. If no, and as I stated, if no, any of those new products. Now, we don't care about the reactants. We know the reactants are soluble. Okay, that's why they're AQ. What we only care about is the new products, whether one of them is insoluble. Okay. If none of them are insoluble, then no reaction. Okay, we got to use the solubility rules. Pressure memory on those. We have the left column, which is the insoluble column, and then the right column, which was the insoluble. So refresh your memory, and there are some exceptions to the halides, for example, that are normally soluble, except for 3 examples. If you look at number 4, silver halide, mercury halide, and lead halide. Okay, so there are some limited insoluble examples. All right, so we have barium nitrate and magnesium sulfate. So in order to attack these problems, the first thing you got to do is the new partners that are created is like we've been doing, you first write them in ionic form. Okay, and so we have barium. Okay, we got the barium is going to partner up with the sulfate. Okay, and the magnesium is going to repartner up with the nitrate. All right, so before I put them together, I put them into ionic form. So I got the barium, which we know is a +2 ion. Okay. The sulfate is an SO4, go to your polyatomic ion table. And so now we have here, if I can put the barium and sulfate quickly together because it's a one-to-one relationship here. Okay. Now, also, I can look at the sulfates, which is number 5. And I can determine whether my new product here is soluble or insoluble. Sulfates are normally soluble, except if you have calcium, strontium, barium right there, insoluble. So this guy, I can very quickly say, there it is. SO4, solid. Okay. All right. My other partner would be magnesium, which is a +2, it's a group 2 element, and the nitrates, which are a -1. Okay, so that means I need 2 of these guys, 2 nitrates. So its formula is Mg. This is the new formula of my products now. Mg parentheses NO3 2. If you recall that all the nitrates, number 3, are soluble, regardless of what the metal is. So this guy here is soluble. Okay, now, so we have to write the new products and put them in ionic form and then put them together to make the new compounds. You will see that most of the time, once you do that, that the balancing just falls in place all by itself. Let me clear it up and we bring this, finish up this last slide here. And there is what we just went through. Okay, we wrote everything in ion form first. Then we put them together with the correct number of cations and anions. All right, let's double check. Are we balanced? Well, we got a sulfate here, 1 sulfate here. We're balanced. Balance these with the follow the polyatomic ions, okay? Nitrates, we've got 2 nitrates here. Guess what? We got 2 nitrates here. 1 magnesium, 1 barium, 1 barium. Lo and behold, boom, you're balanced in this example. Okay, reaction just by default balances itself out. It's simply because the cations, both of them, the barium and the magnesium ions, both of them are negative 2. They kind of fell into place. Anyway, let's stop it here. And we have this slide 26. We'll stop it here.